and your cameras, right?
Everyone turn your book to page 159.
The power,
The power of the water and wine.
Water and wind. So we're going to learn how wind and water are used to create electricity and energy and stuff like that. Okay? Everyone on page 159, and let's read winds and...
6.3, we already do it.
Yeah, you already did 6.3. We're doing 6.4 right now. Winds and sails. Through God's provision, the sun's heat causes air to move and produces winds. The sailing vessel makes use of the kinetic energy of moving air as one of the earliest engines. Okay, quick question real fast. We learned about kinetic and what was the other energy?
what?
We learned about kinetic energy and what was the other one?
Potential.
Potential, very good. Which one is the energy in motion, kinetic or potential?
Kinetic.
Kinetic, very good. So we have potential, kinetic, potential, kinetic, potential, kinetic. Okay. All right. Ancient people such as the Egyptians, Phoenicians, Greeks, and Romans built sailing ships whose sails caught the wind and carried men and cargoes across the Mediterranean Sea. King Solomon, too, and later some of the kings of Judah kept fleets of sailing vessels. In modern times, next page. However, other sources of energy, steam power, diesel power, and nuclear power, have been used in the place of wind pushing on sails to propel vessels through the water. Some smaller boats and pleasure craft though, still use sails to harness the power of the wind. So smaller boats still use wind. But now we have stuff like engines and stuff like that, so we don't have the need for all of that. Okay. Another early use of wind came with the invention of the windmill. Do you guys know what a windmill is?
Yes, it's a thing that it does.
It blows, the wind blows on it. It's kind of like a fan that doesn't move. And so when the wind blows on it, it'll start to move. And then from there, it produces energy because it's moving and it makes a charge in the back. The modern windmill or wind turbine consists of a wheel of blades or sails that is set on a horizontal shaft or pole. The wind whirls the windmill's blades and the wheels turns the horizontal shaft. The vertical shaft is connected to a mill, wheel, a water pump, or an electric generator. In Europe, the Dutch made special use of the windmill to drain the waters of the North Sea from their lands. During pioneer days on America's wind-swept Great Plains, ranchers and farmers depended upon the windmills for pumping water, for grinding grain, and later for generating electricity. After about 1930, the use of windmills for generating electricity declined, so they don't really use windmills much. During the 1970s, however, scientists and engineers again became interested in wind as an energy source and began designing and building vertical axis wind turbines. One of these devices, the Darius wind turbine, named after its inventor, George Darius, looks like a huge egg beater. So you see that picture right there?
Yeah.
That's the Darius wind turbine. Its long blades are curved in a way that allows the turbine to make use of wind coming from any direction. This design, however, was not been as successful as the modern horizontal wind turbine. The water wheel. Muscles get tired and winds stop blowing. Is there another source of energy enabling men and machines to do work? One such power source, discovered by man long ago, is the motion of water rushing downhill or flowing downstream. Flowing water has enough energy and force to move things, from heavy logs to huge barges. At least 100 years before the birth of Christ, the Greeks and Romans thought of using the power of moving water to turn the blades of a water wheel. They mounted their water wheels on frames overlooking a river and connecting them to millstones. Blades on the outside of the wheels dipped into the river and spun around as the flowing water struck against them. The water wheel rotated a shaft which caused the millstone to turn and grind grain. Poor blinded Samson would certainly have welcomed such a device instead of having to be chained to the grindstone in a Philistine prison. Okay, water wheels and sawmills. In medieval and early modern times, the water wheel also supplied the energy for sawing logs and boards at sawmills. Lumbering was the first important industry in colonial America. At first, the colonists sawed boards over a pit using a two-man saw. One man gripped the end of the saw above the log, and the other man stood in the pit to grasp the end of the saw below the log. So they would move like this. There's a giant saw where they go like this. The one would pull, and the other one would push, and then one would push, and the other one would pull.
Mister, I'm sorry because my father was passing.
You're okay. Okay. The colonists soon began building sawmills near rivers where the force of the flowing water could turn a water wheel and make the saw move. Water-powered sawmills were used until about 1830, when steam power replaced water power as the chief source of energy in factories and mills. Water wheels in early factories. Now, hello, Mark. Are you reading? Nope. I'd definitely be paying attention if I were you. Monse, if you are using your phone to do other things besides be in this class, I would advise you not to do that. The same goes for everyone else.
No, mister, I was reading.
Okay. All right. Water wheels in early factories. Before the 1700s, most goods were produced by hand at home. Families and merchants alike relied upon the spinning wheel with its production of some thread at a time, and upon the slow labor's hand loom for the manufacturing of clothing and other textiles. Then four inventions, the flying shuttle and the spinning jenny and the water frame and the power loom, revolutionized the textile industry. The spinning jenny and the water frame were machines for spinning yarn, and the flying shuttle and the power loom were devices for weaving cloth. Except for the steam-powered loom, all these machines were hand-operated or used the power of water, moving water in the water wheel. For this reason, many of the earliest textile factories, or mills as they called, were built alongside rivers. The water wheel supplied the power to turn a main shaft, which through a system of gears and pulleys made the machines work. Okay. Look at that picture on page 161. You see it? All right, so the water is coming down this way, and it's falling on the wheel, which causes the wheel to turn. So it's pushing on the wheel, so it turns. And then inside of that, there's connected with different kind of mechanisms that link up like that. And so as this one starts turning, this one will start to turn as well. Or they'll be like that. So as this one turns, this one will turn, which causes motion and allows the machines to be run by water. And so instead of it having to be pushed by hand or moved by hand, no, it's run by water. Okay. You guys are going to have to do comp check 6.4, but let's move on to the next one.
Mister, that is quick, Mister.
Mister, there is a movie of that of the comprehension check 6.4.
Really?
Yes, I already looked it.
Cool. Okay. Let's have John Carlos. You read for me 6.5.
Water, ice, and steam. That is right.
Yeah.
Water, ice, and steam. The three states of matter. Everything that takes up space and has mass is matter. Material systems and objects such as trees, house, and clock are made of matter. Thoughts and ideas are not made of matter. Matter can exist in three basic forms of states: solid, liquid, and gas. A solid has a definite shape. Liquids and gases have no permanent shape. They will take the shape of the container they are placed in. They are called fluid because they can flow from one place to another.
Keep going.
Liquids are thicker and heavier than gases, and they have more of a tendency to stay together than gases do. If you were to tip over a glass of milk, the milk will pour out in the stream and form a puddle on the table of floor. But if you were to tip over a glass filled with nitrogen gas, the nitrogen would not fall but instance will mix with the surrounding air. The tendency of gases to float away and spread themselves out thinly in their surrounding is called diffusion. Liquids may also diffuse if they are mixed with other liquids.
Very good. Angel Omar, again, why is your camera off? Hey, thank you. All right. So there's three states of matter: solid, liquid, and gas. Solid has a definite shape. Liquids and gases have no permanent shape. That's why water, it's a liquid. So if I spill it, it's gonna go wherever it wants. Whereas a solid, like the water bottle, is gonna stay there. Who's next to read? Monse, go for it. Changes in state.
Change in the state. Matter can be changed from one form to another by either heating or cooling it. The temperature at which a substance changes from a solid into a liquid is called its melting point. The reverse change from a liquid into a solid occurs at the same exact temperature, but in this case, we call the temperature the substance freezing point is this. The term melting point and freezing point, then, are just two different names for one single temperature. Each substance has, however, its own unique temperature at which it will melt and freeze. For example, water melts and freezing at 32, but mercury, a liquid that has been used in thermometers, melts and freezing at 38.
Negative 38.
Negative 38.
Very good.
Another pair of terms is used to refer to the temperature that marks a boundary between the liquid and gaseous state. A substance changes from a liquid into a gas at its boiling point, and from a gas into a liquid at its condensation point. Like melting and freezing, boiling and condensation occur at the same temperature for any particular substance. Water boils and condenses at 212, but mercury boils and condenses at the much hotter temperature of 637. Most substances cannot exist naturally on Earth in all the states. For instance, substances that are normally gases do not turn into liquids unless they are made very cold. We say they have very low condensation points. Oxygen, the gas we breathe, does not condense into a liquid until it is cooled to 297. It is a good
Negative 297 degrees Fahrenheit. Let's stop right there and let's talk a little bit about it, okay? Okay, what is it called when a solid changes into a liquid? What point is that called?
Middle point.
The what?
Middle point.
Melting point. So, like when ice turns to water, that's its melting point. It's starting to get at its melting point. Now, what is it called when a liquid turns into a gas?
Freezing point.
When a liquid turns into a gas.
Another one.
Evaporate.
Which one?
No.
Say it again.
Evaporate.
No, not evaporate. Yeah, it's evaporate, but it's a point. What point?
Conservation point.
Air.
Not evaporation point.
Boiling point.
Boiling point. That's it. Okay, what is it called when a liquid turns into a solid? What point is that?
Boiling point. No.
Condensation point.
Liquid at its
Condensation
condensation point.
point. Sir.
Not condensation point, not boiling point,
Melting point.
not melting point,
Freezing point.
freezing point. Okay, and what is it called when a gas turns into a liquid? What point?
Melting
Means
point.
point. Means point.
Okay.
Condensation.
Condens-
Condensation point.
Very good. All right. Who's next to read?
Hi, mister.
Amelia, go for it.
Good. Good thing that temperatures on the earth never drop low enough for oxygen to change from. Do you know that would happen if oxygen have a much bigger can condensation point? Condensation point. Imagine for a moment that oxygen had a condensation temperature of 15. If the temperature of the air drop below 16, oxygen will fall to the ground as rain or dew. Number one will be able to break that before low flows of liquid oxygen will cover the air. In his will, God made oxygen with a low and condensation point so that such disasters could never happen.
Very good. Okay, so what he's trying to say right there is that the condensation point where gas will turn into a liquid. Gas is like hydrogen, oxygen. Oxygen is what we breathe, okay? We need oxygen to be able to breathe because we need oxygen to go to our body. So what it's saying is the moment that it turns into a solid and falls to the ground, we would die. We need it as a gas. We need to be able to breathe. And so its condensation point is so low, it has to be so cold for it to turn into a solid or a liquid that it'll never happen. It'll never happen. We need to make sure it's a gas. We need that it is a gas in order to be able to breathe. Because if it's not, we'll die. Can you breathe underwater? Nope. It'd be like breathing some sort of liquid. It wouldn't work. You need it to be a gas. All right. Yes, Emilia, finish that section.
Some states like iron are solid at normal temperature and must be made very hot better they melt into a liquid. The melting point of iron is 2,175. Think of what life would be like if iron had a melting point so low that it's called melting on a hot summer's day. Your family cars all be nothing but big puddle in that driveway.
Driveway. Okay, so imagine if iron, the metal that we use for everything to build bars, a lot of the stuff we use for houses and our cars, melted the same way that ice melts. The moment it gets too hot, we would no longer have cars. We would be screwed. We'd be in trouble. So it's a good thing that iron, one of our most useful minerals, melts at a really, really hot temperature. So it has to be super, super hot. Have you guys ever seen melted iron? No? It looks like lava. Here, I'll show you a picture. It looks like...
Look that I looked a place that is the most hot of the moon.
of the world.
Yes.
See if I can get it. I'm having a hard time with my computer mouse.
Who will read next, mister?
All right. Let me see if I can find it. This is 7th grade science right here. All right, I'm gonna show you what it looks like, and I want you to tell me what you think what it reminds you of, okay? That's melted iron. The metal we use for cars, that's melted iron. What does it look like to you?
Like volcano.
Like a
Say
volcano.
Spanish.
Exactly. That's exactly it. And so that's what it looks like. So it has to be really, really hot. But imagine if it melted in the middle of the day, your car would just fall down and would be done. Okay.
They have of the volcans.
They do.
Yes.
Okay.
I have the volcano.
That's what it kind of looks like with volcanoes. Really, really hot. Okay. Water's 3 states. Who's going to read for me? Who hasn't read? Peña.
Hello, bar, mister. Oh, hello. But he's laughing.
I'm really sorry, mister.
Water's 3 states.
Water is a very unusual substance because it does exist naturally in all 3 forms. So, solid water is called ice, and water as a gas is called steam. Water in ocean lakes, rivers, ponds, and puddles often freeze into ice in the winter when the temperature drops. Like snow, sleet, and hail are different types of ice that fall from the sky as precipitation. Steam is produced naturally when water deep underground is boiled by hot or melted rock. Sometimes this steam escapes to the surface in either a geyser or a volcanic eruption. Remember that in a geyser, water fills a deep crevice in the earth. The water at the very bottom is changed to steam by hot rock, and the expanding steam blows all the water out of the crevice. In a volcano, steam and other hot gases cause ash and melt rock to explode suddenly out of a crack in the earth.
Keep going.
Volcano and geyser show us the steam has a great deal of explosive power. When steam tremendous power is harnessed, it can perform much useful work for man. Of course, the natural steam found in geysers and volcanoes now is much too dangerous and uncontrollable to be used by man, but steam can be artificially produced simply by heating gas. How this sort of man-made steam and gas and be harnessed to do work. But first we need to look closely at water itself and at exactly what happens when water is changed into steam.
Very good. Okay, have you ever, don't do this. Do you guys know what a spit wad is?
No.
When you take a straw, you take paper and you put it in your mouth. You
No,
make a ball. Then you,
one meter.
No, Peter.
you know what that is?
And 1 meter.
When you
You
take
have
a
a little.
you put paper in your mouth, get it wet, make a ball, and then you put it in the straw and go.
Yes, I have done that.
Okay, so that's the same thing with steam.
I guess, mister.
Steam is so strong and so powerful it builds up and so blows up. So the steam comes from below the earth and shoots up like in geysers. Okay, see that picture of a geyser?
Yes.
There's one called Old Faithful. I want you guys to look that up. Old Faithful. All right?
Y like that.
Shoots up like that. Okay, next page.
264.
Carlos, I want you to read for me. Water molecules in motion.
Carlos, you have your microphone on.
Mister, I want to be in the school for science class because during the school you didn't put us to do comprehension test in this school test.
You what?
I want to be in the school just only for doing science because in the school you don't put comprehension check to do and you just.
Just we do it, just we say the answer.
All right, Carlos, you're up, bud, but you need to turn your mic on.
Okay. Water, like many other common substances, is made of tiny particles called molecules. These molecules never stop moving. They vibrate back and forth. They bump into each other. When water is in the form of steam, its molecules fly about and bounce around like millions of miniature rubber superballs. You know already that kinetic energy is the energy of motion. We could say then like every other moving object, this vibrating, jiggling, spinning, flying, bouncing, or bumping molecules have kinetic energy. Now, the amount of kinetic energy that water molecules have is very important because it determines whether the water is a solid ice, a liquid, or gas stream. Ice is a special sort of crystal in which the molecules are arrange themselves in layers of interlocking hexagons. A hexagon is a shape with 6 sides. The large open space in the middle of each hexagon makes ice lighter and more expanded than liquid water. Because ice is lighter, it floats on the top of the water when it freezes instead of sinking to the bottom. Most other substances through the are heavier a solid than to make as liquid. We can easily see why God chose to make ice unusual in this way. If ice were heavier than liquid water, lakes and rivers would freeze solid in the winter, and all the plants and fish in them they will die.
Die. Very good. Okay. Gloria, will you read?
Teacher, I want to get out of the class.
Kenya, Hello Mar left, but I'm not going to let him back in. Gloria, will you read for me the last page right here?
Molecules of ice have very little kinetic energy. They squeeze right up against each other end to end, and a strong force of attraction between the molecules being them in position. The molecules vibrate weakly in their place but cannot move about freely. When ice is heated, its molecules gain kinetic energy and vibrate more and more. After the melting point is reached, the ice turns into liquid water. At the melting point, the molecules vibrate so rapidly that they break out of their fixed position in the hexagonal pattern. The water becomes more dense, compacted, and heavier. As molecules fill in the empty space in the crystal liquid, water molecules are still kept near each other by force of attraction, but they are no longer connected together. A very small amount of space separates the molecules. They can travel freely through the liquid, bumping into each other as they move about. When water is heated, its molecules pick up even more kinetic energy. They vibrate even faster and bounce about more rapidly. After the boiling point is reached, the water becomes steam. Steam molecules are so far apart and fly around so fast that they are not held together by force of attraction anymore. Uncle- Unless the molecules are enclosed in a container, they will diffuse into the air.
Very good. So it talks about how molecules have kinetic energy, all right? And so the molecules of ice have very little kinetic energy. So they stay together. They don't really move. When he heats it up and becomes water, they move more. They have more kinetic energy. And then gas, they have a lot of kinetic energy where they go. Like smoke. That's a type of gas. So it has a lot of kinetic energy and it'll go up in space and fly away. Okay, see this right here, watching molecules move? Yeah, that is your project that you guys have to do this week, all right? You guys have for that.
Welcome, Mister, how many projects do we have for the last week to write?
Only one, I believe.
I do it.
But there are 2 projects in one.
Were there two?
Yes,
But the main one is on page 154.
yes, and the other is 155.
Nope, just 154.
You have
And
a
65, no.
What did you?
Mister, 65, no.
No, just 154.
Okay.
Yeah.
I will do them.
Who just left?
Mm,
Hilamar's gone, yeah. Sander, but he's telling me his Wi-Fi is bad. That's all right. All right, so you guys have to do 6.4, 6.5, and you guys have to do 6.6. That was a short chapter, okay?
Okay.
6.6 is a little. It's little.
Yeah.
It's 2.
I got 6.5.
Of Bible, mister. Let's
Huh?
finish. I will send you the homework of Bible.
Perfect. Sounds good. All right. That's all you guys have to do. Any questions?
No.
All right. Good luck. You guys can do it. If you have any questions, let me know. All right.
Right.
All right. I'll see you guys. Have a good day.
See you tomorrow.
What time do you guys have social sciences?
2.
Oh, right now? All right. Go take a quick little break before you have to get back, okay?
Okay.
Bye.
Peter, I love you that you have a good
You take us out, Ron.
Bye, goodbye, goodbye. I'll take you out.
Like Mrs. Rosales,
She said
my
goodbye.
aunt,
Goodbye.
but she said in Spanish.
Okay. I'll see you guys. Goodbye.
Bye, Mr.